We now look at the second law of thermodynamics, especially how it relates to heat engines. So, before we do that, we have to define two terms. One is a reversible process, and the second is an irreversible process. A reversible process is one in which both the system and the environment can return to exactly the states they were by following the reverse path. What that simply means is that you can undo changes by basically reversing your course of action. So let's imagine I have a cylinder with a piston on top, and I can squeeze the gases in that piston down. Assuming it's insulated, so I'm not transferring heat, I'm not losing any heat to the environment. If I push down, I increase the pressure, I decrease the volume of the gas in that cylinder. Now, if I reverse that process, if I pull up, I decrease the pressure, I increase the volume back to its original state. So by undoing the changes I just did, I can reverse what I have done, bring the system back to its original state. Now, that seems like, well, that's an obvious thing, right? Just undo what you just did and everything will be fine. But processes, changing pressure and volume in a system is tricky. And sometimes you cannot simply go back and do what you just did in reverse direction to get back to the earlier state. Irreversible processes are processes that occur spontaneously in one direction. Now, the example your book gives, and a popular example, is that of perfume or cologne. Imagine I had a bottle of perfume or a bottle of cologne at the front of a room, a large room like the room I'm lecturing in right now, and I open it. Eventually, the perfume or cologne, the little molecules of perfume and cologne, will escape their container and permeate the room. The room will start smelling like the perfume, or it'll start smelling like the cologne. Now, the reverse of that is having all of those perfume molecules spontaneously go back into the jar, into the container, into the bottle of perfume. That will never happen. Or rather, the statistical likelihood of that happening is so ridiculously low, we say that it will never happen. Right? Another example of an irreversible process, shuffling cards. You get a fresh deck of cards. If you've ever bought a deck of cards new, you know that the cards are placed in order. All the suits are together in descending order, from ace, king, queen, jack, 10, and so on. If you shuffle that deck very well, you spend time actually really shuffling that deck, you've created disorder, you've mixed up those cards. Now, the reverse process, basically start shuffling again, the likelihood of you shuffling the cards back into perfect order is so ridiculously small, we say that will never happen. In fact, just those 52 cards in a regular standard playing deck, there's so many possible combinations and orders of those cards that every time you shuffle and you deal out a hand, the chances of those cards in that order existing before is almost zero. So every time you shuffle well a deck of cards, the order of your shuffled deck has never before existed in the universe and will probably never exist again. If you want to see how many possible combinations there are for a simple deck of cards, just find out what 52 factorial is. 52 times 51 times 50 times 49 times 48 times 47, all the way down to times 1. That is how many possible combinations there are for 52 cards in a deck. So, irreversible processes, right? Baking cookies, right? If you take cookie dough and put it in the oven and the cookies bake, you cannot undo that by putting the cookies in the freezer, right, or the refrigerator. Baked cookies don't revert back to dough when you cool them. That's an irreversible process. The second law of thermodynamics deals with reversible and irreversible processes. And what it states is that heat transfer occurs spontaneously from higher temperature bodies to lower temperature bodies. That's the only direction heat transfer occurs spontaneously. It never spontaneously occurs in the other direction. Another way of saying that is you've never placed a cup of room temperature water on your kitchen counter, come back an hour or two later and found it boiling hot. Right? Hot coffee will cool with time. It doesn't get hotter with time. Heat transfers from hot objects to cool objects, not the other way around. That is very important because if you remember our heat engine argument, when we transfer heat, we can peel off a little bit of that heat to do work. However, heat only spontaneously moves from higher temperature bodies to lower temperature bodies, which means for a heat engine to work, we need two different temperature bodies. We need a hot body and a cooler body where heat transfers between them in order to do work. So let's look at a little more detail on the heat engine. So for a heat engine, we can look at this diagram here. So we have some high temperature reservoir and some low temperature reservoir, right? So hot and cold. Now, hot and cold are respective to one another, right? The cold reservoir still might be hotter than what we would consider, body temperature. These just have to be at a different temperature, with the hot reservoir being at a higher temperature than the cold reservoir. Heat then will flow from the hot reservoir to the cold reservoir, but what a heat engine can do is peel off some of that heat transfer to do work. So the cylinders of your car, what effectively happens is gasoline is ignited, which releases a tremendous amount of heat energy. Right? Just burning gas releases heat. We take advantage of that heat release in a closed cylinder, to have the hot gas push on the cylinder, expanding it, pushing a piston up. That is the work done by that expanding gas from the heat released from the detonation of the fuel. Then the cylinder in the next cycle closes, it pushes out the old gas, right, the burnt fuel, and that hot remaining gas in that cylinder is ejected into the fuel, into the atmosphere, right? That's the exhaust of your car. So it goes from the hot reservoir of the hot gas that was detonated in the cylinder. Some work is done, and the remaining heat that was generated by burning the gasoline is spat out into our environment. So the cold reservoir is the atmosphere around us. And then the heat engine again is shown by this dotted line. That's the process of the heat engine. So heat can only spontaneously go from hot to cold. So if these are the same temperature, you cannot do any work, right? If you don't burn gas in your in the cylinders, right? If you don't detonate that gas with a spark plug in the cylinders, if you just have say it's 80 degrees outside, if you have 80-degree gas in the cylinder head, that's all you have, it's not going to do any work. So the work done is the difference between the heat pulled from the high temperature reservoir and the heat dumped into the low temperature reservoir. Or actually, to be consistent, there should be T sub C for cold. Now, how much work you peel off for a given heat pulled from the high temperature reservoir is called the efficiency of the engine. In a 100% efficient engine, all of the heat you pull from the high temperature reservoir will go into work. That's an ideal case. And if we could do that, that would be awesome, right? What that effectively means is no heat is dumped into the low temperature reservoir, which means that regardless of the temperature here, we can pull heat from any system at all and do work. So imagine plugging in a battery until all of the chemical and thermal energy of that battery is pulled out, the battery's at absolute zero, chuck it, get another battery. Be able to use every single possible joule of energy from that battery, both thermal energy, chemical energy, whatever, to do work. That'd be super awesome, but that Can't happen. Some energy has to be dumped into the cold reservoir. You cannot have a 100% efficient heat engine. The most perfect heat engine you can have is called a Carnot engine, and your book describes the Carnot engine. A Carnot engine uses all reversible processes. There's no turbulence, there's no heat loss due to friction. It's an idealized heat engine. So any heat engine made by humans at all has to be an efficiency at or below the Carnot efficiency, the maximum possible efficiency. So the actual efficiency of the engine is the work you get out over the heat dumped in from the high temperature reservoir. If you want to know what the maximum possible efficiency is, here's the equation for that. It's called the Carnot efficiency. It simply states that the maximum efficiency is 1 minus the ratio of the temperature differences between the cold temperature reservoir and the hot temperature reservoir. So, for this to be 100%, or an efficiency of 1, the cold temperature reservoir has to be absolute 0, which of course we don't have for normal engines. The high temperature reservoir has to be infinitely hot, which again we don't have for reasonable engines. I mean, infinite heat would melt anything it was in, right? So engines would just melt. But the bigger this temperature difference, the smaller the ratio is, and the higher your maximum efficiency is. If there is no temperature difference, if T sub C and T sub H are the same, this ratio is equal to 1. 1 minus 1 is 0. The efficiency is 0, meaning you don't have an engine. You don't have a heat engine if the high temperature and the cold reservoir are the same temperature. So it's one of the reasons diesel engines are slightly more efficient than traditional gasoline engines, is diesel engines run hotter. And since they run hotter, the cold temperature reservoir is the same, it's the atmosphere. But since diesel engines typically run hotter, they're slightly more efficient than gasoline engines. So engineers and auto manufacturers and every other, anyone who works with engines is trying to get as close to the Carnot efficiency as possible. This Carnot efficiency cannot be exceeded for a heat engine. It's just not possible. It violates what's called the second law of thermodynamics, and we'll talk more about that in a little bit.